Hello everyone, my name is Harrison Canning, and for my news presentation I wanted to focus on brain control of bilateral neuroprosthetic arms. This is from a study that came out of Johns Hopkins, which happened in late December of 2020, so this is still pretty topical, and this is one of the most advanced applications that I've seen. So for a quick summary, this was brain control of two robotic arms. These arms can be tactile, so touch, and proprioceptive, so that's spatial sensation, knowing where your arms are in space, information back to the user directly through their brain. And this is the first time that an interface of this complexity has been used. So here we see some training. You can see that the user, Buzz, over here on the right, is thinking very hard to control these arms. And so he's training to grasp different arms and move his arms around, move the robotic arms around. And towards the end, it got really, really specific. So he was actually able to pick up a fork and knife with these arms and then go over, cut a slice of bread, and then here he is bringing it to himself to feed himself, which is really, really exciting and incredibly impressive. And in his own words, this is what it is like to feel through the prosthetics.
What kinds of things have you felt? Like, what kind of range of things have you felt?
Um, some of the, I mean, I felt anywhere from, and some of it's hard to explain what it really feels like. Like some of it is a pulse. Like I said, it kind of feels like when you do the blood pressure. The other one is the actual pressure, where it feels like somebody's grabbing your hand or your finger. Um, some of those are pins and needles, like when your arm falls asleep type thing. Um, Even down to the best way I could describe it would be like somebody takes a pencil point, like a dull pencil point, and is touching me in certain spots. Some of these I've, uh,
So we'll go ahead and pause it there because he goes on for a couple more minutes. So not quite like normal touch that we would have, but the fact that we can turn pressure sensors in a robotic arm into something that you can actually interpret as sensation is pretty amazing.
What kinds of things have you felt? Like, what kind of
Let's go on to the next one there. So why are they doing this? Well, the purpose is to restore quality of life to people who have limited motor and communication abilities due to ailments such as paralysis. So Buzz does have some paralysis, although it could be worse, I suppose, and neuromuscular disorders like ALS or muscular dystrophy. So in the United States, there are 5.4 million people with some form of paralysis. There are 15,000 people with ALS, which is a progressive neurodegenerative disorder where you don't have the ability to, or you over time lose the ability to control your muscles. And that's very similar to muscular dystrophy as well, which takes a couple of different forms. And there are 250,000 people in the United States with muscular dystrophy. And severe cases of this can be referred to as locked-in states. So we see a girl over on the right in a locked-in state. And so this can get to the point where they actually can't speak or really move much of their body, but they're still conscious. So it's very scary, that type of thing. And so the consequences of that, of locked-in states specifically, and paralysis and ALS to a lesser degree as well, is that it can cause tremendous psychological trauma for both the patient and their family members, as now they are essentially locked into their body. Um, this also creates a huge financial burden on the family because now the person needs help eating, feeding, going to the bathroom. So that either means that that someone in the family is staying home from work to care for them 24/7, or they're hiring a caretaker, both of which are very expensive. So the current solutions that we use are not great. This has been the standard that's been used for a while, although I will talk about some other technologies. And so basically here you have the person, because they can usually still move their eyes. So you have the person look up in one of these groups, and then if you're looking through the middle, you can kind of tell which group they're looking at, and then the user would say like A, B, C for that top box, and then you would blink or give whatever indication you can when you hit the right letter. And same thing over on the right, just with different actions like showering, brushing teeth, things like that. Another solution that's popped up recently is eye tracking. So this is a Tobii eye tracking system that can detect where he's looking. And so that can be useful for computer control and some basic communication applications. But a BCI solution could theoretically be better because theoretically it could be the most intuitive method. If you're just thinking and something's happening, like that's the best system you can create probably. So this does not require so if you had one of these devices on and it was helping you do something, like let's go back to Buzz, who has these robotic arms, um, then you wouldn't need the constant assistance from a caretaker, which would be empowering to the person and, again, maybe lessen that financial burden. So you can imagine a wheelchair with some arms coming out and then also a computer system for communication, and that would be really, really cool. And there's some other studies using actually the same interface up there to do other things. So as I mentioned, here's some cursor control for a computer. And then here is brain-computer interface controlling a exoskeleton. So you can imagine how all these can combine together to really help the patient out. But how does this work? So to give us some context, let's just talk about where the electrodes are and different types. So we have three different types. We have invasive, semi-invasive, and non-invasive. So starting on the non-invasive, we have EEG electrodes, which sit on top of the scalp. No brain surgery required, but pretty low resolution, hard to work with. Then we have these semi-invasive ones, which are under the skull, but they sit on top of the brain, so they don't damage brain tissue. And then we have these arrays of little pins that actually penetrate brain tissue, but these are the most accurate, of course, I guess the most dangerous as well. And so that last one, the fully invasive ones, are actually what's being used here. And there are 6 of them. They're called Utah arrays. Each one has 96 electrodes. And there are 2 placed in each one of these modules, of which Buzz has 3 placed on him. So this is quite a procedure, and I have never seen that many used in a brain-computer interface study before, so that's exciting. And so where they were placed are on the 2 motor cortices, so there's one on each side. The one on your right controls your left arm, the one on your left controls your right arm, and then the somatosensory cortex controls that sensation of touch. And so the 6 are laid on top of these so that Buzz can move his arms around and feel. So the process of this is a 3-step process of collect, encode, deploy. So they do that training that I mentioned before, where they're having Buzz think about doing one task, try to do one task. Of course, the robot doesn't know exactly what to do in the beginning, but if he keeps trying to do that task enough in the same way, they're recording all of that, then a machine learning algorithm, which is this encode part, can learn to figure out what he wants to do. And then eventually they can connect that to the prosthetic arm to actually have real-time control of the arm when Buzz wants to do a specific thing. So here is a quick clip of what that training process looks like. So you can see these are actually virtual arms, so that Buzz doesn't break the system when he is training. And you can see he's starting to get it in this here. There are some misses like we see in the beginning of the video where his arms are kind of crossing right here, but overall this is how he trains. And then again, just to reiterate in the beginning, after that training, some pretty incredible dexterity was achieved with these arms, where he was able to cut bread and feed himself. So if we have the greater context now of knowing who this is for, someone that might not be able to move at all or maybe even communicate, again, you can think about how powerful this would be if they had access to these arms 24/7. So in terms of the authority and validity of the source, this comes from Johns Hopkins University, specifically the Department of Physical Medicine and Rehabilitation in collaboration with the University Applied Physics Laboratory and the Laboratory and Department of Neurology and Neurosurgery. So quite a accomplished group there, and Johns Hopkins, if you don't know, is one of the most acclaimed medical and research institutions in the country and the world. But one thing to point out in terms of ethics is that this is primarily funded by DARPA, which is the Defense Advanced Research Project for the U.S. military. And so while I certainly trust Johns Hopkins University, there are other motives that DARPA is going to have, of course. So this could have potential ethical issues because DARPA could eventually look at this to enhance their soldiers as opposed to just help out people with disabilities. And then, as you learn more about brain interfaces, there could be other abuses. There's always like the mind control and ideas around that. So those are always concerns. And then in terms of a connection to the course here, so there are 3 that came to mind specifically. So cyborgs, human machines, So that one, that was the movie that film that we watched. That was about an hour, and this really made me think of that the first person in there who actually did have a brain implant that was allowing him to hear different colors because he was colorblind. And so that still is addressing an abnormality like these are, but we're starting to blur the lines a little bit. And then, the rest of the devices that were in there really were not addressing a malady. They were instead adding function. And so we could imagine that maybe, like, I could get another one of these arms and be like Doc Ock and have two arms coming out, and that might give me advantages. So is that allowed? And that's a good conversation to have. Which brings us into the next one, which was really talking more about genetics, genetic engineering, but still the same thing applies. If I could allow myself to see ultraviolet light or, just experience different sensations. Like I know of someone that hooked themselves up to the stock market and felt vibrations that correlated to that. You could start to have certain advantages. And so that's a conversation to have and that we've talked about in the course. And then this last one, cyborg experiments with Professor Kevin Warwick. He talked about a very positive view of enhancing the human body with technology. So again, that's a good connection to this. And the BrainGate system that he used, although he used it peripherally, that's actually the same system that we see Buzz using in this Johns Hopkins example. So in terms of my interests, I run a club here at RIT called the Neurotechnology Exploration Team, and so we're not working with any invasive stuff, but we are working with EEG, so non-invasive brain sensing technologies, work on a bunch of different projects. Here I am over here, and then down the bottom left as well. So that's a lot where that interest comes from. I also run a YouTube channel with my business partner called the BCI Guys, BCI standing for Brain-Computer Interface, where we make content on this sort of thing. So I'm really excited to have the opportunity in this class to talk to you guys about brain-computer interfaces, because this really is my passion, and it's a really cool course to be able to have that outlet. So here's some sources. You can pause if you are interested. These are for all the images, and these are for the content that I covered. Thank you very much.